Now that we have defined Stirling numbers and found a recurrence relation for them, let us try to find a closed form for the Stirling numbers. Theorem for 0 smaller than or equal to k smaller than or equal to n, s and k, which is the Stirling number of the second kind, is 1 over k factorial summation t is equal to 0 to k choose t, negative 1 to the power t, k minus t to the power n. Okay? Proof? Induction on n. Induction on n. N is equal to 0. Well, if you plug in a 0 in everything, you get 0 to the 0. So everything becomes 1. 1 is equal to 1. And that checks out. Okay? For n is equal to 1, okay, let's actually do n greater than or equal to 1. And we are going to do it in two cases. Case k is equal to 0. Then Sn comma 0, which should be equal to 0, is equal to 1 over 0 factorial times 0 to 0, which is 1. This is equal to 1, times negative 1 to the 0, which is also 1, times 0 to the n, which is 0, and so all of this is equal to 0. And so that also checks out. And so we move on to case k is between 1 and n, k1 smaller than or equal to k smaller than or equal to n. And we are going to assume that, oh, this is true for everything of n minus 1. Okay, so we are assuming that it is true for 1 to n, n minus 1, 0 to n minus 1, and we are going to prove the result for s is equal to n. So by assumption, by a previous thing, we have seen the recurrences n minus 1 k, right? Where this is equal to 0 if one of them is, if k is greater than n minus 1, k minus 1 is greater than n minus 1, or k is greater than n minus 1, or k minus 1 is negative. Well, expanding this out, since both of these are for n minus 1, I can assume the result for these. Summation t is equal to 0 to k minus 1, k minus 1 choose t, negative 1 to the t, k minus 1 minus t to the n minus 1, plus k over k factorial, summation t is equal to 0 to k choose t, negative 1 to the t, k minus t to the n minus 1. Okay, both of these are to the power n minus 1, but one of them is k minus 1 over t, k minus 1 to, minus t, the other is k minus t. What we're going to do is we are going to do a change of variable. We are going to say t prime is equal to t plus 1, or t is equal to t plus 1. Okay, and if I replace t by t plus 1, then when t is equal to 0, it becomes t is equal to 1, top value becomes k, this becomes k minus 1 choose t minus 1, negative 1 to the t minus 1, k minus t to the n minus 1, plus k over k factorial, summation t is equal to 0 to k minus 1 choose t, negative 1 to the t, k minus t to the n minus 1, right? Now I have both of these terms as k minus t to the n minus 1. I am going to pull all of that out. 1 over k minus 1 factorial is exactly equal to k over k factorial. So I'm going to write it as k over k factorial times summation t is equal to 0 to k choose t minus k minus 1 choose t minus 1, -1 to the t, k minus 1, choose n minus 1. And you will note that, oh, why can I say that this sum starts from 0? Here my sum started from 1. How can I combine these two? Well, if I include t is equal to 0, my first term has k minus 1 choose -1, which by definition of choose is 0. So I can add the t is equal to 0 because that term is going to be 0 anyway. Okay? So that is the reason I can have both of these sums starting from the same place. And so this we know is equal to k minus 1 choose t. We have seen this before. And so we want this to be equal to 1 over k factorial summation t is equal to 0 to k choose t, -1 to the t, k minus t to the n, right? And so if I compare these two, need k times k minus 1 choose t to be equal to k choose t times k minus t, and that is very easy to check. Okay, and therefore you can just expand these out. You will get that they're exactly the same by induction. I have that Snk is equal to 1 over k factorial summation t is equal to 0 to k choose t, -1 to the t, k minus t to the n. Okay, great. Now, what is the practical application of Snk? What is the combinatorial idea? So given sets x comma y with x is equal to n, cardinality of x is equal to n, cardinality of y is equal to k, lemma, the number of surjective functions, the number of surjective functions f from functions from x to y, so just x to y is given by summation t is equal to 0 to k choose t, -1 to the t, k minus t to the n. Okay. Proof? Well, if you have summation like this, the general idea where you are doing -1 to the power t, where it's flipping, the general idea is use inclusion, exclusion. Okay, so we are going to define, let S is equal to set of all functions, from x to y. Well, then the cardinality of S is equal to, well, how many things are there? There are, for every element in x, you have k choices in y, right? And so you have a total of k to the n possible functions. Define for one smaller than equal to I smaller than or equal to k, I is equal to set of functions from x to y minus I. Okay, which means that, oh, these are the functions that do not have I in their image, so they definitely can't be surjective. Therefore, we want a1 complement, a2 complement, ... intersection AK complement, right? Well, we have seen how to do such a thing before. For S, which is a subset of 1 to k, define AS is equal to intersection I in S, AI, which is the set of functions, is equal to set of functions is equal to set of functions from X to Y minus the set S, right? And so therefore cardinality of AS is simply, well, how many elements are there now? That for every element in X there are Y minus S, however many those are, to the n. Every element in X has Y minus S number of choices, right? And so the total number of functions is going to be Y minus S to the n, which is exactly equal to, well, k minus absolute value of S to the n, since the size of Y is k, size of S, I'm denoting absolute value of S. Therefore, by inclusion exclusion, intersection A1 bar, intersection A2 bar, dot dot dot, intersection AN bar, AK bar, my bad, is equal to summation S, small s in 1 to k, subset of, subset, not element, subset of 1 to k, absolute value of AS times -1 to the power S, right? Now, how many S are there? How many ways are there of choosing? How many possible sizes of S are there? Well, the size of S can be 1 to k or 0 to k. So I'll denote the size by t. So t goes from 0 to k. How many S are there of a given size? Well, the number of S is the number of ways of choosing t elements out of k, right? Which is exactly k choose t. And then the size of each of these is k minus t. Size of S is t. Size of S is t, and I get times -1 to the power t, right? Did I make a mistake? Oh, sorry. K minus t is the size of S, and this is k minus t to the power n, because that is the number of functions I get. Right? AS is k minus t to the power n, and so I get this, which is exactly what I required. This is t is equal to 0 to k. Well, that is exactly the formula I have, right? And hence we have that the number of ways of getting a surjective function from x to y is exactly this sum. And a corollary of this is for 0 smaller than or equal to k smaller than or equal to n, first, k factorial times s n k is equal to the number of surjective functions from 1 to n to 1 to k. right? Because S and K is exactly this previous sum is equal to K factorial times S and K, right? So that's part one. Part two, K factorial times S and K is also equal to the number of ways to put n distinguishable objects, distinguishable objects into K distinguishable boxes, leaving no box empty. Leaving no box empty, right? Why? Well, just label the boxes 1 to K. Now you're trying to find a surjective function from 1 to n into 1 to K. Because surjective would mean that no box is empty. The number of things you're putting in each box is the number of elements in 1 to K. Are the elements that are getting mapped to that element of K, right? And S and K is then equal to number of ways to put n distinguishable elements, distinguishable objects into K now indistinguishable boxes. Indistinguishable boxes, leaving no box empty. Because what is the difference between 2 and 3? If I make my boxes indistinguishable, then I can permute the boxes, right? How many ways do I have of permuting the boxes? Exactly K factorial. I can't tell if I have put 2 things in first box and 3 things in the second, or those exactly same things in the 3 things in the first box and 2 things in the second. The boxes are indistinguishable, right? So I just divide by K factorial, which exactly gives me n factorial. Proof by lemma. Okay, so that ends the part on Stirling numbers of the second kind.